Welcome to a tutorial of ProfLearn YouTube channel. In this particular video, we're going to look at space physics and some of the areas that you really ought to understand as far as space physics concerned. So we're going to have a candid discussion on different questions that have been asked in various years, so that end time you are going to be given questions related to this. You can be able to work them out. If you're new to ProfLearn, consider subscribing and also check in the description so that you can be able to download this particular paper from my Patreon page. So one of the questions that was asked in the most recent years is to describe how a black hole can be formed from massive stars. So something that you need to understand here is that there is different life cycle or life stages of either a massive star or a low mass star. But when we're talking about a high mass star, it means that during the initial stage for the star formation, the nebulae, a lot of mass of the nebulae was pulled together by gravity and then compressed, which resulted to the fusion of hydrogen and hydrogen to form helium. When there is enough pressure and temperature, then fusion reaction begin. And once the fusion reaction begin, we cannot say that the star now is born and it becomes what we call a protostar. So once a star becomes a protostar, it continues burning helium, hydrogen, and when in the process, as hydrogen being fused together to form helium, then there will be now outward force that is being created from within the star. The moment now this continues, then when the outward force is equal to the inward force, the star now moves to a stage which we call a main sequence star or a stable star. The star now will continue at that the main sequence star or the main the stable stage star for a period of billions of years. And when all the hydrogen is used up, the star now collapse due to gravity, and then again it's compressed, temperature, enormous amount of temperature and pressure is created again, but the fusion now that begins is helium and helium will start fusing. Now once all the helium has been used up once the fusion of helium and helium has started, the star is going to generate an enormous amount of heat, and then it's going to expand to become a red giant. And after a red giant, or if all the helium is used up, the star will run out of fuel, and then it now moves to another stage. It cools down to become a white dwarf, which could further to become a black dwarf. Now those are life stages of a low mass star. So I would like to write that so that for low mass star, for a low mass star, it's going to follow the following stages: protostar, that is a baby star. It moved to stable star, and this is the stage where the sun is currently. Then we have a red giant. When all the helium is used up from the red giant, it becomes a white dwarf, and finally it cools to become black dwarf. So those are the stages of evolution of a star. Then now if we are talking about a massive star, massive stars, they do not follow the stages as shown as stipulated on the low mass star. They start of course as protostar, and at the protostar stage, this is where gas and dust particles have fused, and the hydrogen and hydrogen fusing together now is a young star or a baby star. So for massive star, you'll have a protostar, you'll have a stable star. Now instead of being a red giant, it becomes super red giant. Which now move to another stage which we call a supernova. Supernova, which is basically an exploding star. Which is an exploding star. From the supernova, this star explodes either to be a neutron star or it can become black hole. Now, the star will either become one of the two. It cannot become two of them. So if the star was just massive, it will become a neutron star. But if it was very, very massive, it will become what we call a black hole. So here candidates were told to describe how a black hole is formed from a massive star. This is when all hydrogen is converted into helium, the star expands and become a red giant, which explodes as a supernova, and a black hole forms at the center of the supernova. Those are the stages that we are going to state about the formation of star. So next we need to look at what is meant by light year. 1 light year is a distance light travels in 1 year. Is a distance light travels in 1 year. So in the event that you are supposed to calculate what is this distance here equivalent to, what is it equivalent to in kilometers? So what you need to understand is that we have given the definition that 1 light year is equal to distance traveled by light in 1 year. But in a year, we have 365 days, 24 hours, and we multiply 3,600, we convert to seconds, and this is the speed at which light moves. So which means we are using the formula that distance is equal to time times speed. Distance is time times speed. But now, since we want our speed to be in our distance to be in meters, we need to convert the time to be in seconds, because speed of light is basically 3 times 10 raised to power 8. I need to just cancel this. Yeah, so this is the speed of light, which is 3 times 10 raised to power 8, times the time in 1 year. This is time in 1 year that we have at this given point. 365 days times 24 hours times 3,600 seconds times the speed that we are having. Then now, if you have the distance, how many light years do we have in this question? We have 7,800 light years. That's why you can see I multiplied by that. But for me to convert this to kilometers, we are going to divide by 1,000. Yeah, so, but something that you need to understand is that 1 light year is equivalent to 9.5 times 10 raised to power 15 meters. And also we can be able to say 1 light year, which is also is equals to 9.5 times 10 raised to power 12 meters. So that is what we call 1 light year. So if you are told 7,800 light years, so that distance in kilometers, you are going to take sorry, yeah, this is kilometers here, but this one is meters. So the lower one is in kilometers, this is in kilometers. But if you want to find the distance in meters, you are going to use 9.5 times 10 raised to power 15 meters. So which means that if you want to know what is this equivalent to in kilometers, you will take 7,800 times 9.5 times 10 raised to power 12 kilometers, which is going to translate to this. You don't have to follow this step, but you only need to understand what is the equivalence of 1 light year. But the most important thing you need to understand is that distance light year is distance traveled in 1 year, and you can be able to get distance from time times speed. So which means that you can be able to convert the time 365 days into seconds so that you can be able to multiply by the speed of light. Well, that is exactly what I did here to show that we can move now to the definition of a galaxy. We can say a galaxy is a collection of billions of what? Stars. And the sun is in the Milky Way galaxy. Something else that also you need to put into consideration, remember that the sun is in the Milky Way galaxy, and a collection of billions and billions of galaxies form what we call the universe. So yeah, so also there's a question, what is equivalent to 100,000 light years? So you are going to say 1 light year is equals to this. Because this is in kilometers, we are going to because we mentioned in the previous question that also 1 light year is equivalent to 9.5 times 10 raised to power power 12 kilometers, and this is in meters. So meaning that for you to convert 100,000 light years, you are going to take 9.5 times 10 raised to power 12 times 100,000 so that you can be able to get your answer being equivalent to that. Moving further, we can also look at astronomers. You know, astronomers try to study how far different celestial objects are, so they can be able to know how far a galaxy is. And for them to do that, they use the change in wavelength, because light observed from distant galaxy undergo Doppler effect, so they display a longer wavelength, and change in wavelength is the one that is used to determine the speed of a galaxy, whereby you can be able to use the formula change in wavelength over wavelength of light on Earth is equal to the speed of a galaxy divided by the speed of light. And this is basically what we call the Doppler equation. So one observation that allows the galaxy moving away to be determined, the speed at which the galaxy is moving away, is the change in wavelength that is used. And state one different observation that is used to determine the distance. This is basically the redshift. State how the speed of the galaxy and their distance state how speed of galaxies and their distance from Earth are related. This is basically what we call Hubble's law, and Hubble's law is basically V is equals to H naught D. Yeah, so V is the speed of the galaxy, H naught is the Hubble's law, and D is the distance of the galaxy. So speed, you can see from this equation, speed is directly proportional to the distance. So the farther the galaxy is, the faster it's moving, and that is actually the relationship that we're gonna use at that given point. I use this value to calculate, estimate the age of the universe. Age of the universe is actually age. If you are told to work out the age of the universe, you are going to say that age is equals to 1 over Hubble's constant. So the moment you are given Hubble's constant, you can be able to determine the age of the universe. And in this case, we know Hubble's constant is this. That is Hubble's constant, 2 times 10 raised to power negative 18 per second. Then you are going to say 1 over 2.2 times 10 raised to power negative 18. So we can be able to put that in the calculator so that we can see what does that really give us, what does it translate to in the spectrum of the age of the universe in seconds. So this is trying to tell us since the universe was created, how old is it until now? So 2.2 times 10 raised to power negative 18, and if you work it out, you're going to get this value here, which is basically 4.5 times 10 raised to power 17 seconds. That becomes our final answer. State the name of the planet that is has an orbit further away from the sun than Venus. We can talk of Earth. Yeah, Earth is far away. That's set one planet that has orbit closer to the sun than Venus, and that is Mercury. Mercury is a bit closer. Yeah, a bit closer to the Earth. Venus has an average radius of this and orbital period of this. Orbital period. Period is time taken for the planet to go around a complete orbit. So time taken for it to complete to make a complete orbit is what we call the orbital period, and this 220 Earth days. Now, calculate the average orbital speed. So something that you need to put into consideration as well is that orbital speed is the speed at which, an average speed at which a planet really orbit around the sun. So to find that, you are going to use the concept 2 pi r, where r is the radius and t is the orbital period. So in the event that we want to calculate this, we know that this is the radius, right? And this is the time period, right? And in this case, we want our speed to be meters per second, so meaning that this distance must be in meters and time must be seconds. So it will be 2 pi times the radius that was given here in meters, and we were told 220 Earth days. So meaning if it's 220, we have to this is days, so 220, it means that this is days. In a day we have 24 hours, and for us to convert to seconds, we multiply by 6 to have in minutes, and then again multiply by 6 to have in seconds. So basically, whatever that we did at the denominator is to ensure that we have our time in seconds, and if you work it out, you are going to get your answer as shown there. State the relationship between orbital speed and distance from Earth. So something that we need to be very clear here. If you have the sun at this particular point, yeah, we know that the orbit of planets is actually elliptical, isn't it? Yeah, a orbit of a planet is elliptical. And so if we have another orbit here, so this planet that is here, planet X, and this planet we can call planet A. This planet A will be moving faster around the sun because it's closer to the sun. So the shorter the distance, the faster it's going to orbit around the sun, and the further away it is going to be slow, because there is weak gravitational force pulling together, and the gravitational pull is the one that is responsible for it to orbit around the sun. So the further a distance, the slower the orbital speed. So that is what we call the relationship. That is what we call the relationship in this particular case. Then we need also to talk about comets and how a comet move around, and we need to look at the orbit of a comet. So the first thing I want to do is to ensure that I have the sun well situated at this point, and then around the sun there is going to be a orbit like that. Yeah, so let me just ensure that it's a bit cleaner. Yeah, orbit of a comet is very elliptical, very elongated, and the way to identify that, to ensure that you don't confuse it with the orbit of a planet, is that the orbit of a comet, the sun is towards one end, one edge is towards the edge, but here the sun is approximately through the center for the orbit of a planet. But orbit of a comet, you realize that the sun is gravitated towards one end. So you need also to know that when the comet is very far at point L, it means that when it's far, it's going to experience a weaker gravitational pull, and then it means it's moving, it will be moving slowest speed. It will be moving at a lowest speed. And here, when the comet is very close to the sun, I can even use this point here, the comet will be moving fastest here, because it's very close to the sun, so it's going to experience a larger gravitational pull. So when the comet, so we are supposed to identify here and say when the comet is closest to the sun, it has, I need to ensure that this is well written. Now let's check, did I include all the keywords? Explain your answer in terms of conservation of energy. State how the speed of the comet changes, the speed changes as it's moving around. As the comet moves around the sun, kinetic energy is converted gravitational potential energy. When it's farther away, it has low kinetic energy, hence it moves slowly. As it moves closer to the sun, its potential energy is converted to kinetic energy, and it moves faster. And it moves what? It moves faster. So the closer a comet is to the sun, as it's moving from point L to point X, it means that the speed will be increasing because it will be experiencing a greater gravitational pull. You need also to understand how long the Earth takes to orbit around the sun, and we know that it takes 365 days. So if you are asked the time or the period it takes for it to move from point E all the way to point F, it means this section is a quarter of a full evolution. So which means that this is going to be 365 days times a quarter, and that is going to translate to 91 days. This is going to take 91 days because EF is a quarter of the entire orbit or a full revolution, and in a full revolution it takes 365 days. Identify the position where it's summer. Remember, it's summer when a given section is facing the sun, so which means it's summer at point F, because at point F, that's where X, let me just erase this so that you can be able to see, that's where X is directly facing the sun, and it's winter at H because now at this given point, this point X is facing away from the sun, so it will be winter at that given point. Finally, we also have a question to do with orbital speed, and in that way you can realize that here we have the formula you use, but in this question we were given the orbital speed and then we are supposed to calculate the average radius. We are talking about average radius because the orbit of a planet is not a perfect circle. It's kind of elliptical, it's oval, so which means that whichever radius that we are going to be talking about, is basically the average radius. Here the radius is larger compared to this, so that's why we are talking about the average radius. So meaning that you are going to substitute what we have, and remember that the time that you shall use here must be in seconds for you to work it out. So in 365 days you have to multiply by 24 times 60 times 60 so that you have in seconds, and if you do the substitution you are going to get your radius to be 6.0 times 10 to the power 10 meters. Don't forget that other objects usually orbit other objects that usually orbit around the sun. We have a comet, we have what we call dwarf planets, we have meteorites, we have meteors. So those are objects that usually orbit. So we shall stop there so that we can be able to prepare for another one. So check the link in the description so that you can be able to see other questions that have been asked before, so that you can be able to get to learn more from Proflan. Now then, you can check the link in the description, that we can be also access the link that is going to be taking to part 2 of space physics. We shall be having part 2 of space physics, so that we can be looking at other questions that been asked. So for instance, here you can see you are told that Jupiter and Earth are planets in the solar system, and then you are supposed to talk about the characteristics of those particular planets that are closer to the sun. Jupiter is very, very far, so which means that it's gaseous. Those stars that are a bit far, they are gaseous, and those that are very close, they are rocky. You can also be asked to define gravitational field strength. This is going to be is a gravitational force, or is a force per unit time, per unit mass rather. And if you are you run short of time, you can be able to write it in terms of a formula. You can be able to earn the mark. So the amount of gravitational pull that exists between two objects will depend on the amount of gravitational pull that exists between two masses or two celestial objects depend on two factors. We can talk of the mass of the objects involved. The larger the mass, the stronger the gravitational pull. But also we can talk of the distance. The larger the distance, the weaker the gravitational pull. So here we shall talk about the mass. State and explain the difference between orbital speed of Jupiter and orbital speed of Earth. Remember, Jupiter is very far, so which means the orbital speed of Jupiter is slower than the orbital speed of Earth. And we are going to back that by saying that Jupiter is far away, so it's going to experience a weaker gravitational pull. Then in that way, it's going to have a slower, it's going to be orbiting, it will be orbiting at a lower speed. And we mentioned that in the previous set of questions. Explain which one of these planets is closest to the sun. In order to see which planet is closest to the sun, look at the surface temperature. Those planets which are very close to the sun, they are going to be experiencing high temperatures, and you can see that that one is what is going to be what is going to be B, and you can see it has what a surface temperature of 623 Kelvin. And for you to convert to degrees Celsius from Kelvin is the temperature in Kelvin minus 273, and that is going to be negative 180. Object falls through height of 2 meters. State and explain which planet object falls 2 meters in shortest time. Remember, the speed at which an object falls to the ground or toward the ground depends on the gravitational pull. So the stronger, the greater the gravitational pull, the lower the time it takes. So if the time is very, very short, it means it has to be the strongest gravitational pull. And where are we having a stronger gravitational pull is this one. So that is going to be A. And we're going to say it's A because it has greatest gravitational field strength, and the acceleration due to gravity is going to be greater. Then it's going to take the shortest time possible. Then the next one is about stages and evolution of stars, which I mentioned that this is a massive star, so it's going to move from a protostar. It becomes to be a red supergiant. As it expands to be a red supergiant, it explodes to become a supernova. And inside the nebula it contains hydrogen, and which means that once it explodes, it can either become a black hole or it can become a neutron star. Now those are the stages that you really need to understand. State the quantity and the brightness, and the quantity, the brightness of a supernova in a galaxy is used to determine. So when a supernova explodes, it produces a lot of light in space, which astronomers can be able to use in order to determine how far is that particular galaxy is. So basically you need to understand that so that you can be able to understand that distance of a galaxy can be determined by the brightness, how bright a supernova is. Define a light year. Already we have mentioned that a light year is a distance traveled by light in 1 year, and already we have mentioned that in the previous section. All right, so in this particular question, Good. So the next question here is saying that it takes 490 seconds for light to travel from the sun to Earth, and how can we be able to work out the distance between the sun and Earth? Because we are given time, it means we can be able to use the formula speed times time for us to get distance at that given point. And end time also, you are given a graph like this and you are expected to work out Hubble's constant. What you need to understand that Hubble's law states that V is equals H naught D, and this equation is the form Y is equals to mx plus C. So this is Y is equals to mx. So H naught is the gradient. H naught is what? Is the gradient. So meaning if you work out the gradient of this particular graph that we have here, that is going to give us Hubble's constant. And remember, to find the gradient is rise over run, so you can be able to find a section, define a region, and then you work out the gradient, and this is rise, and you shall use the run at this given point. In that way, rise over run is going to give you the gradient, and that's going to be that value there. Define what's meant by redshift. Remember, light from distant galaxies are observed to have an increased wavelength, and this increased wavelength is what is than the measured wavelength on Earth, and this is exactly what is termed to be that is what is termed to be a redshift. And this redshift is the one that is now used to determine how fast a galaxy is moving away from the universe or from Earth. And next we were asked to identify the orbit of a comet. Something that you need to remember here is that the comet has a very elliptical orbit, a very elongated orbit, a very stretched orbit, which is quite elliptical, but the sun is towards the edge of that particular orbit, and that is going to be B. So meaning that we have a comet at this given point here, and then the sun is here, and then this other one, this is the orbit of a planet because it's orbiting the sun. Explanation why we say this B is because the sun is not at the center. Yeah, it's not at the center. Now describe and explain how the motion of the comet changes as it orbits the sun. We say the orbit of a comet, speed at which the comet is orbiting the sun depends a given section where it is. So which means that the farther it is, the farther it is, the slower it's moving. So which means that you could have said that a comet travels faster when it's closer to the sun because its gravitational potential decreases and the kinetic energy increases as the comet comes closer. And as it comes closer also, the gravitational pull becomes stronger, so it moves faster. But here we want to mention that. State what's meant by 1 light year. Already we have mentioned that is the distance traveled by light in 1 year. Determine the distance meters between the comet and Earth. Already we were given some more information that is 6.6 light years, but we know 1 light year in meters is 9.5 times 10 raised to the power 15, which we had mentioned in the previous part. So if you work it out, that's exactly what you'll get. So according to accretion model, as per the accretion model, those planets which are very close to the sun, they are usually small and rocky, but those that are very far away from the sun, they are usually big and they are usually big and gaseous. They are usually big and gaseous. They are usually big and gaseous. All right, so all planets were formed when the cloud and gas dust collapsed due to gravitational force, and the rotation material in the cloud forms what we call the accretion disk. So if you want to understand much of this, you go and learn about the accretion model theory model, so that you can be able to understand this concept that I've tried to highlight here. Calculate the distance. So if we are talking about time, it takes time taken for light to travel from the moon to the earth is 1.3 seconds. So calculate the distance. So for you to calculate distance, you use speed times time, and then we know speed is 3 times 10 to the power 8 times this. You are going to have your answer as 3.9 times 10 to the power 8 meters. So basically that's what you're going to do there. And also we are given Whirlpool galaxy is 2.3 times 10 raised to power 7 light years, and we are supposed to calculate the speed of the galaxy. Of course, when you have distance, the formula to use to calculate speed of a galaxy is V is equals to h naught, where h naught is Hubble's constant, and Hubble's constant, of course, we know is this value, but this distance has to be in meters. So meaning we're going to multiply this light years times 10 raised to this light years, this answer we have here, times 9.5 times 10 raised to power 15 meters, so that we can have the distance in meters. And then if you work it out, we are going to get to find the speed of the galaxy. V is the speed of the galaxy, h naught is Hubble's constant, and this, how far is it? But the time, the distance that was given here was given in light years, so that's why we could go this step of multiplication, 9.5 times 10 raised to power 15. And I believe towards the almost last question, we are going to talk about cosmology. Cosmology is trying to study of the origin of the universe. So according to physics, IGCSE Cambridge Physics, you are going to focus on origin of the universe based on Big Bang theory. Big Bang theory is the origin that tries to explain is the theory that tries to explain how the universe originated. So according to Big Bang theory, it claims that the universe originated as a single dense point which expanded to become whatever that we have right now. So which a bit been proven by scientists, and because of the presence of microwave background radiation that is always present in the environment, and also the observation that the galaxies are moving away, it's an indication that the universe is still what? The universe is still expanding. So the question is, states when CMBR was created. CMBR is the background microwave background radiations. They were created shortly after. They were created shortly after what? Big Bang. State and explain how the wavelength of this radiation has changed. Since then, the wavelength has stretched. They have become longer. Yeah. And then calculate the speed of the orbital speed. Already we have mentioned in other questions how to work it out. You are going to use 2 pi r over t, and state how the average surface temperature of the planet changes as the distance increases. Remember, the farther it is, the farther a planet is, the less amount of heat is going to get from the sun. Lastly, but not least, we are going to sketch the orbit of a comet around the sun. We say that the sun is gravitated to one end, and the orbit is basically elliptical. And you are supposed to draw an L. Lowest speed is where it's very, very far from the sun. That's where you have the largest distance. So this is where it's going to have lowest speed. Explain why the speed of the comet changes as it travels around. I've already explained the previous section that total energy is equal to GPE plus kinetic energy. So the law of conservation apply. So as the comet approaches the sun or comes closer to the sun, its gravitational potential energy is converted to kinetic energy, so it speeds up. It moves at a very high speed. So when it's moving away, when the comet is very far, gravitational kinetic energy is converted to gravitational potential energy, so it's going to slow down in that process.